Hello, welcome back to SOH, the best office hours in the universe, because you are part of it and you should get better than I. So let's see if you catch me. A customer, this is 2023, not today, we're already 2025, I know, but there was 2023 AP Calculus AB. You have to go back to the past. And question number one, you need a scientific calculator like Desmos or else to solve some of these questions. But you always need to set them up correctly, otherwise you may lose half of your score. Let's read the problem through, let's see what we need to do, and in a minute or two we're done. You can try to solve it yourself or continue listening to those questions that you would like to know more about. And yep, let's go into it. So a customer at the gas station is pumping gasoline into a gas tank. Good. The rate of flow of gasoline, is modeled by a differentiable function. That's very relevant. Okay, it's differentiable. That will allow us to use derivatives or even second derivatives or the mean value theorem, just a heads up, where f of t is measured in gallons per second. Wow, we have units. Guys, we have units. Be careful or you're cooked. Don't forget the units, okay? Gallons per second. And t is measured in seconds. Well, that's kind of consistent. Good. Selected values of f of t are given in the table. Beautiful table that I put here for you, okay? Now, using correct units, interpret the meaning of this quantity in the context of the problem. And then use a right Riemann sum with three subintervals, of these three subintervals here, to approximate the value of this quantity here. So, well, first of all, what is f of t? Is the rate of flow, is gallons per second. And you integrate, so gallons per second multiplied per seconds. This is seconds, right? You get gallons. So this is the amount of gallons that have been pumped between t equals to 60 seconds and 135 seconds. That's it. And then we will approximate the value, see how many gallons are there. So that's for A. B, okay, must there exist a value of C in between 60 and 120 such that the derivative is 0? Well, yes, but how do we know that? Because of the mean value theorem. The mean value theorem can be applied to a function that is continuous, but this function is differentiable. So it's not only continuous, but its derivative is also continuous. And using that, you will be able to use the mean value theorem to get to know this. Notice that for 60 and 120, the values here are 60 and 120, they are the same, so we will get that, yeah, the numerator is 0. Anyway, you can look at it later on in my solution or by yourself. Now, question number C, the rate of flow of gasoline in gallons per second can also be modeled by this function. So we have, a table or a function. And there is this cosine of t squared, whatever expression it is, it looks like, wow, quite complicated, but very nice. And then only between 0 seconds and 2 minutes and a half, 150 seconds. Using this model, find the average rate of flow. So the average of a function is always the average of a function, any function, over some interval over t equals 1 over t. You start to count some initial time, in this case is 0, right? But anyway, and this is the average. You can see that the units here, just a count. The units is going to be time divided by time, so still the units are going to be units of f. So the solution of this is going to be in the units of f, which were gallons per second. And then using this model, find this quantity, so how the rate of flow changes in time is kind of the acceleration, right, of the flow of gasoline into the tank, and interpret the meaning. So if it's positive, it means that the rate of flow is increasing. If it's negative, the rate of flow is decreasing. And well, we have to compute it, and for that we will use a scientific calculator. So you can use maybe Desmos, right, and find it out. Okay, so you can try it, get another 5. And come back to see if there is any other comment that you like, or continue to see how we solve them. Let's go ahead. Okay, so first question, the meaning. Well, so again, so you have an integral where f has the units, f is measured in gallons per second, right? So you have something that is gallons divided per second, But then dt is time. Doesn't matter the d means small. So it's a small amount of time, but still is time, so it's seconds. So they cancel out, so what you get when you integrate, so you get gallons. So therefore this quantity has gallons. So between 1 minute and 2 minutes and 15 seconds, that's the total amount of so this is the amount of gasoline, of gas, pump into the tank between t equals 60 seconds and 135 seconds. That's the first part, interpret. Now let's compute that. Well, for that we have this beautiful table, but be careful. We have the right. Okay, but then let's begin with the intervals, right? We have these intervals here, so we have these 3 intervals, and let's see. So we have what are the intervals that we consider? So don't be careful not to use more or less of what you need. So these are the ones that we need. Now always compute the difference between the intervals. 30, that doesn't change. All the problems are the same. 15. And what it means right is that you're going to choose the right. So in this interval there are 2, left and right. So right, left. In this other interval there's left and right. So right, left and right, right. Okay. So now let's compute this quantity. Let's do it in red. Okay, even though it's correct. So what we have is this quantity here, and it's going to be so the difference of 30 multiplied by this function is g. How do they call it? F. Okay, I don't. Okay, doesn't matter. However they like to call it, I'm happy with it. F of 90, and then 1 by 1, so 30, and then again 30 times f of 120, and finally 15. Remember that the difference is 15 only. F of 135. You can use a calculator, but let me just do it for fun. So we have, this is 0.15 plus 30 times 0.1 plus 15 times 0.05, and well, this is just 4.5, this is 3, right, and this is 15, that is 0.75. So in other words, it's 8.25 gallons. Very, very, very important to use the units. Otherwise, you may get half of your score down, and we don't want that, right? Okay, so done. Let's move on to the next one. Yeah, that's it. So about 8.25 gallons. The next one is if there is this value where the derivative is 0. So if there is a moment where when the rate, this is the acceleration of the rate. So the rate is given, it may be increasing, and then it will be 0 and then decreasing. Probably is basically the idea that you start pumping, then you pump more and more, and then you start to slow down that pumping before you remove it, right? Something like that. Okay, so the mean value theorem. What is the mean value theorem? So the mean value theorem, you can use other theorems like the Rolle's theorem too, but the point is the following, and it's very useful to have this one. You only need one of them, so this one is more general. If f is differentiable, if a function is differentiable in AB, then there exists a number c between a and b, it's not a or b, such that the derivative at that point, let's remove that little dot here, is equal to this. So basically this is the average slope, right? And then there's a number that in between that exactly matches that average slope. There's a proof for that is very cool. If you want to know more about it, write in the description. One can just throw it, and it's very intuitive. But it's a very useful result in many applications of mathematics. Anyway, so for that we also need that the function is continuous. So it's always good that you say everything, Honestly, it's kind of repetitive. If a function is differentiable, if f is differentiable, and we have that in this problem, then f is continuous and its derivative is continuous. So indeed, if they even tell us that the function is differentiable, we know it's continuous and the derivative is continuous. But if you want to get all the points right, you want to get all the points, not just to be right, but get the points, You should rather say that f is continuous because it's differentiable. Okay, so if f is differentiable, we have the mean value theorem. We also have that f is continuous, so we can apply this. Okay, it's kind of super repetitive, but that's how it is, man. So now f prime of c is going to be what's a and b, these two guys. Remember that in the table, we can look at the table in a second, but we have that 60 on the table. We have that these two have the same value. So this is 0, 0. So that's it. Yes, there is a c between 60 and 120 such that the derivative is 0. And congratulations. Okay, basically it's reversing the rate of flow to maybe higher to lower. Let's see. The next question, maybe it's related to that. Yes, it says that the rate of flow of gasoline can also be modeled. So it's the same, it's like the table, but now it's a function. Instead of a table, we have a function. And between 0 and 2 minutes and a half, remember these are seconds. Using this model, find the average of flow. Ooh. So the average of a function is 1 over the time interval, 150 seconds, the integral between 0 and 150 of all this function. So always write the setup, because otherwise, you will get some points down, and we don't like that. Okay, woohoo! So how do we do that? Well, in this case, yes, we need a scientific calculator. Let's use Desmos to see how much it is. Remember, 3 digits. That's what they ask you after the period. Okay, so let's see what is Desmos. What do we have here? Let's write this function. What do we have to do with this function? We have to do this. Oh, and then compute the derivative later of this function. So why don't we write the function, right? So we have it for later on. You could use the variable x. I'm going to use t to show you that you can also use t instead of x. So, but then, it's a little bit, we have to go like this. And then we can do like, what is the parenthesis here? Okay, well, let's begin with our, with our function here. So let's define the function. Is t divided by 500? Yes, 500. Okay, 500. Whatever you want. Now let's move to the next thing, and then we have cosine. Be careful here because we have all these parentheses, right? And it's kind of a little bit confusing. So we have the cosine. So let's do a first parenthesis here, but we need another parenthesis, and this one has t divided by something. T divided by 150. Okay, congratulations, 150. And then we close the first parenthesis, we square, well, not here down, right? We have to move a little bit there. We close it, we square it, and then we close it again. That's amazing. So now we have this function here. What do we want to do with this function? Well, compute this average. So it's going to be 1 divided by 150. And then the integral. So you can just type integral here, int. And oh, here it comes. I like that from Desmos. You don't need to go to functions. So then 150, and then here, which function? Well, g of t, right? We have just defined g of t. This way you have everything a bit more organized, and you can reuse your results. But you need the dt. Again, you can use just the keyword dt. Amazing. Wow, look at that. So you get the result. And after, so 0.126, right? 0.126. Now, what's missing here? What's missing? Units. Always, if there are units, so important. So this is gallons. This function was also modeling the flow of gasoline in gallons per second, and is the average. So also going to be gallons per second. Okay. So we have this. Every single second there is about 1.26 gallons inside the tank. Awesome. Now, what's the last one? Yes, the last one. Well, g prime of, so you see, you go to g, you need the prime, right? But it's not in the keyword. So you have to go to functions and scroll down a little bit. They hide it a little bit, but here it is. We found it. And then what time? 140 seconds. Okay, 140 seconds. And what do we get? Just with Desmos, we get like minus 0.00, and then the first digit here would be 1, right? But what we have is let's see, let's make sure we have, this is the function yes, and we have here the, let me check that we have all the squares here. Oops, right? Yes. cosine, yep. Oh, this is 120. So 120. Okay. So indeed, this result here should be 0.095. So let's change that. 0.05. 0.05. This will happen for sure. So yes. So let's do this. This is indeed 0.09 and then 6, right? 96. And then when we go here, then we have this other result, 0.005. Then the units of this is gallon per second, but again per second, because why is that? Because you have that G was gallons per second, but G prime is the derivative of G with respect to time, so you have another time. Okay, that's why it's per seconds, and it's negative. So using interpret, so basically what this means is that the rate of flow of gasoline, of gas, into the tank is, and here comes the keyword, right? The keyword is decreasing at a rate of this amount, and that's it. End of the story. That's what you have to take into account. Always units. Make that if it's negative is decreasing, if it's positive is increasing, and that's basically it. And yes, we are done. Thank you so much. See you in the next one. Get better than I, for sure. Bye.